Is the presentation visible?
Yes, sir.
Okay. So friends, good afternoon. Let us continue where we left yesterday. We have been discussing about activity diagrams in UML. This is one of the important behavioral diagrams which primarily talk about the algorithmic part, the procedural part of the system. So we have seen already seen three behavioral diagrams. So one was the top level use case diagram, which is just abstraction of what the end user or the significant actors in the system have to do. And then we saw the sequence and communication diagram, which are in terms of the a client server model as to how the different objects in the system interact through messages. In sequence diagram, we saw messages in the temporal order, though specific clock time was not considered here, which is a part of the timing diagram. And in the communication diagram, we talk about how the objects communicate between themselves, the spatial relationship of them. So that kind of sets up the interface and interaction. And in the activity diagram, we have started discussing that given a particular request or a message when the execution has to happen, then what is that activity, or what are those activities that are going to happen? What are their control and data flow and so on? So probably somebody is not mute. Could you please mute yourself? Please mute yourself. Some noise is coming. So we saw the basic notion of an activity, the partitions, swim lane, and so on, and the activity ages. That there are ages between activities which show that basically in a way that they show kind of a control flow from one activity being completed and automatically the other activity is starting. And we saw that there could be object ages as well, where from one activity to the other some object might also flow. So we will have more details on that. We will first today we will talk about specifically the role of control objects and actions in the activity diagram. Right. So first we start with the control. So this is just for a quick recap. We went through this simple activity diagram yesterday. Now, in terms of control, there could be a variety of control nodes uh, as activity nodes, and they are used to coordinate the flow between other nodes. So we have initial node, the flow initial node, the activity final node, the decision nodes, merge nodes. Some of these you have seen, but we will formally define. And we have fork and join nodes to take care of concurrency. So these are the basic kind of nodes that you can see. There is an initial node here, which you have seen the notation. The diamond decision node, where some inputs come in, and based on a decision, the control goes out. Then there are merge nodes where multiple control flows come in and get merged, and one control flow go out. We'll see variants of that as well. We have final activity node. That is when the activity actually gets completed. And in between, we are showing two kinds of nodes. One is called a fork node, which forks an activity into two or more activities. So these are kind of concurrent activities or parallel activities that are happening after a fork node. So when the concurrent activities happen, then they will need to be put together through a join node. When the concurrency ends, then they will be joined in a single control flow through the join node. So we will look into specifics of that. So initial node you already know. I will skip that. A flow final node. This is not an activity final node. This is a flow final node, a particular branch of flow in the control, may end. There may not be anything else to do. So then the incoming control will be terminated by a small circle with a cross inside. And we have the activity final node in which the activity altogether ends, which you have already seen. Decision nodes naturally is a open diamond where you have two or more decisions going out, and on each one of them you will have a guard. The guard will say the condition under which the control will go on that decision node, which is very typical of what we do in flowcharts. So order accepted, order rejected, or say this is a ternary decision node where the control come in, the priority being 1, it goes here, priority being 2, the second one, and everything else goes in the third one. So that's a decision node. Similarly, you have a decision input behavior node. So these are kind of, so you have guards, but this says that the guards will be evaluated based on this condition. So typically in a flow chart, we will write some condition inside that diamond, right? That is, we say x less than 5. We write inside that. Here, we write it as a decision input. So in inventory less than minimum. So that's the standard in the UML. So if the inventory less than minimum condition is true, then the control will go in this path. If it is false, then it will just be terminated. That flow part will be terminated. So it could also be that it is not a decision input given here, but this is a decision input flow. That is some other decisions involved in a bigger diagram, which if that control comes in, then I know what are the guard values, and based on the guard values, so it is either a simple condition or a condition arising out of a flow which decides the guard values, and we take decision nodes according to it. We have a merge node where multiple 2 or more controls comes together, and a single outgoing flow happens, right? So that could be control or object flows, as we'll see. So here is a typical merge node. The characteristic of merge node is to be a non-blocking one, which means that if I'm merging 3 flows, then if the control comes through any one of them, then the control will flow out. I mean, it can come either from this. So it's kind of a OR condition, you can say, exclusive condition. If the control comes from any one of them, the control will flow out, and that is a non-blocking part. So diamond is with 2 or more edges entering and a single activity leaving out of it, right? So that's remember this part, that this will distinguish it from the join node later on. That the merge node is non-blocking. It's a OR condition of input controls. Often times, so after a merge, there could be a decision. So if that is there, then it is possible to merge these two in the diagram as a merge and decision node. So here the control could come through any one of these. The control flows out based on the guard condition on the decision node. So that's just a shortcut in the diagram that you can have. You can show them as separate nodes also. Semantically, it does not make a difference. So kind of an example. So the control comes in here, which is a decision node, making the decision. And these are the guard condition. So you are checking for a block creation entry. And so that is starts with word count being 0 is one guard condition. Another is word count is between is greater than 0 and less than 1000. That is between 1 and 999. And the other is it is 1000 or more. So you say that here there is no block to be put. Here there is a valid block which need to be saved. And here the block is just too long, so it cannot be processed, right? So there are 3 different actions that are activities that are involved here. And each one of them finally merge in this node. So from here, from the decision, you can easily see that the branch out could happen on any one of these, and wherever the branch out has happened, obviously the control will not flow through the other branches. And so wherever the exclusive OR of wherever the control comes from, the merge node then proceeds, merging the control and displays the status. Right. Now let us think about concurrency. So it is the concurrence is a property that distinguishes an active object from one that is not active, right? So it is kind of saying that, well, what is an active object which can concurrently happen? So the first thing in concurrency is a fork node. It's again a control node written in this manner that has one incoming edge. So the control is coming out and multiple outgoing edges. So it says that on each one of these outgoing edges, unlike the decision node where the control goes to any one of them exclusive, here the control starts on all of them. So concurrent flows, three things are going to start happening at the same time, right? So a line segment with a single activity entering it and two or more edges going out of it. This is a combination with fork node. First, let's do fork node. With the join node, first let's do join node. So this is a fork node, and that is how it distinguishes from a decision node where the control flow out is exclusive on the guards, and in fork node, it is concurrent on all the output control edges. The join node is where a control node has multiple incoming edges, two or more, and one outgoing edge. So the join node is blocking. Unlike the merge node, where the control can come from any one of them, here the control has to reach the join node from all of these paths, right? So concurrently, you started doing three things. And you are saying that I can proceed further only when all those three activities have actually ended, right? So this is a blocking node. So it will block till all of the controls have come. So kind of you can say that notionally, where the merge node is an OR, exclusive OR, here the join node is an inclusive AND, that all of the controls have to be there. So one way to visualize this kind of a control flow, which works for sequential as well as concurrent model, is to think that as if there is a token that is going along as the control flows. So what happens is, I'm going back one slide. So what happens is you have a token here, which if it arrives this node, then the node triggers. That is, the control goes to the next stage. So here the token is triplicated. 3 copies of the token are made, and each one of them is given to the control flow. So the token keeps passing through that control flow. Now, in a fork node, for a join node, the join node waits for the token to arrive from each of the nodes. Whereas in a merge node, it waits for any token to be received. So you can, this kind of a token kind of view helps to understand the concurrency, because in sequential, where you have decision and merge nodes only. So I just hold on for a second. There's some disturbance. Just hold on. Sorry, some repair work is going on in the neighbor's flat. Okay. So the token view really helps because you can conceptualize this. This token is not a physical one. It's more like a conceptual one, that the token is coming through this flow, and when the token arrives a node, the node decides what to do with the token, as to whether to pass it on to the output or hold it back. So the join node will hold back all tokens till all tokens have arrived. Right. This is kind of a This concept actually came from a earlier model, precursor to this. Of some of the earlier models that gave rise to the UML diagrams. There was a very seminal work called Petri nets. You can look up. It's very nice model. So that was kind of one of the initial models which tried to create, model the behavior of concurrent systems, and that used this kind of fork join node concepts and the token concepts, and this part is actually borrowed from there, right? So if you're interested, you can look up that Petri nets. There was a lot of work done earlier on this, but now it has got become a part of the activity diagram. Now, naturally, you can you can merge the, you can combine the decision and merge nodes together. You can combine the join and fork nodes also together. So which means that here it's first a join node. So the tokens have to arrive from all the three for this to trigger. Otherwise, the token has arrived here, control has arrived here, it will just wait at this node. So once the token has arrived from all these three, then this node triggers, and it triggers as a fork node. So it replicates the token and puts it on each one of these outgoing links, and the control continues. There could be some conditional ones also. For example, you can say that the join specification is sum is greater than or equal to 2, which means that you don't have to wait for all the three tokens to come. You can trigger if you have at least 2 tokens. So you're saying that the sum is greater than or equal to 2. Any 2 tokens come, you can trigger that. So there could be different kinds of such conditions which are possible. So you can see that in a very seamless manner, the sequential as well as concurrent flows are being stitched into the activity diagram. So that's the most important part of the control nodes here. So some examples due. This is coming in. Then you have a fork node. So it is forking into 2. So it is kind of trying to put together a system, possibly a laptop or a PC. So you do on one side, you prepare the case. One side is casing in which it will go, and the other activity is prepare the motherboard. So you're saying that these are concurrent or parallel activities. So the tokens placed on both starts, different teams possibly doing on that. There is a kind of shovel kind of stuff shown here, which is prepare motherboard. So this means that this particular activity has a bigger activity activity chain that will go on, right? So prepare motherboard is install the CPU, install memory, and then that activity is over. So that is the detailing of that, whereas prepare case does not have such detailing. Whenever there could be further detailing of an activity, this symbol will be used. Now we say we have a join node. The join node will wait for both these to be over, so that the later process can start. So you have to have the case as well as the motherboard, so that you can install the motherboard in the case, right? And then you install the motherboard, then you install drivers into that, you install video card, sound card, and so on, and that goes on. So but this basically shows what is the kind of parallelism that you can model. Okay. This was our earlier shopping activity diagram, which was sequential. This is okay. So we look at another product process as a concurrent diagram. So there's a product process that we are trying to get into the activities. So there are multiple swim lanes. The first swim lane is between the location, based on the location. So it is either New York or London. The activity in London has further swim lanes of marketing and manufacturing. Okay. And the swim lane on New York has only one activity, that is design. Right? So that is the swim lanes going on. So they go on in parallel. Now in the design, you are designing the new product, that is activity. And only when the designing of the new product is over, the marketing or manufacturing of the product can start, right? So it has to get over, but they don't wait for each other. I mean, once you have the design, you on one side, you start manufacturing the product. On other side, you start marketing the product. Because if you wait, if you first manufacture and then wait, then market, then you will be late to market, right? You will have a lot of inventory manufactured. If you first manufacture, if you first market and then manufacture, then you would have brought up a lot of hype and expectation about the product, but people would not be able to get the product. So you start these processes in concurrent, in parallel, and that is what is getting triggered here. Look at something interesting happening across the swim lanes also. That once the product is designed, it needs to go to the manufacturing. So there is a activity flow here, which is basically an object flow. What is that object? Object is a design that has been created, right? So you have an object node here. You can see this is rectangle, not rounded corner. So there's an object flow coming from design new product to manufacture product. So on one side, this controls the triggering of manufactured product based on the concurrent triggering of the market product. On the other side, the object product specification, the design, is passed on to the manufacturer, right? So this is a very typical kind of situation you will always have in that process. Like those of you who were there in the discussion in the laboratory yesterday, you would have noticed similar kind of situation as to producing the design, producing the test plan, producing the test cases, doing the implementation, doing the testing, try to model them in terms of activity diagram. You will be able to see that from the specification, a part of the test plan can be independently developed along with the design. So those are concurrent activities. But certain other parts of the test plan may need the design, because that is design specific testing, which is conditional to the design being finalized and so on, so that you can try to do activity diagrams based on that. Now here, coming back here, you have marketed the product, you have created the market for the product, you have manufactured the product. So when both of them have happened, that the market is created as well as the product is there, only then you can go ahead and sell the product. So you do a merge node, you do a join node to do that. So it waits for tokens on both, and then you go over to selling the product. It's a very simple example, but kind of, I like this example because it kind of gives a situation which we need in a variety of activities, starting from software development itself to various of the real world situations that we need to model. I think we have seen this. So this is just processing of the order that are being looked at in more details. For example, you have a process order control coming in, control flow coming in. Here is a object flow coming in as requested order. And when that comes in, then you go into this decision node. And if order is accepted, then you go to fill order. If the order is rejected, then you come to the end, right? So your decision node based on the guard condition. Now, when you fill the order, there are two things that you start doing at the same time. One is you prepare for the invoice. Invoice is the billing to charge. And at the same time, possibly a different group start preparing for shipping the order, taking it from the inventory, doing packaging, putting labels and all of that. The send invoice will have an invoice object, which is sent for accept payment. So this is an object flow. So you have the object invoice. And only when both of them have happened, that is, you have accepted the payment and you have shipped the order, only then you join here and go on to closing the order. So this is the other path through which you can close the order. Of course, bypass path is if the order is rejected. So shows another very typical way of how you use the concurrency in the activity diagram. Right. So we have discussed the control node situation. We have given some examples on that. So let us move on to doing the rest. Let me just stop once, and because concurrency was a new concept. So let me check if there are any questions. Any questions, friends? Because you haven't done things like operating system yet, right? Or for that matter, distributed systems, right? Am I correct?
Yes, sir. Okay. We haven't done it.
You haven't done all that. So this will become very handy, particularly when you study operating system. These kind of models, you may not use them as UML diagrams. Depends on how you are doing the design, but you will see that these last two diagrams that we are doing, the activity and the state machine diagrams, are very useful in terms of variety of concurrent and sequential system design. So this is the basic. And you will also do a number of parallel processing or concurrent processing, multi-threaded programming, multi-process situations. You will see that there are absolutely equivalent. I mean, there are process libraries which have fork and join APIs available for doing equivalent operations. So you can fork a process into two or more processes. So they start in execution in concurrency, or you can do it at the thread level. You'll understand the difference when you do operating system. And once you have done, say, 2 or 3 threads doing 2-3 tasks, you will have to bring all that control together in the master through some kind of a thread join or a join of processes and so on. So we are just modeling those kind of situations which are very much real world. So
yes. The form of activity diagrams, like as far as I could understand, they follow the CSP model, right? Because you said the concurrency is via message passing.
Yes, primarily.
But then right now, like the more popular one is the Promise framework, like that's using JavaScript and.
No, you are no. So this is Deep, right?
Yes.
So Deep, you are getting into more into the implementation aspects of these models, right? This is activity diagram is a behavioral diagram that is at a conceptual level, right? Now, whatever framework you use to implement the respective distributed system could vary, but conceptually you are doing the same thing. Conceptually you have multiple activities getting started at a certain point on a certain incidence, and you may have situations where you have to wait for multiple activities to complete before you can go further. You are just modeling at that.
That's level. A lock,
right? So that's that's a semaphore, right?
Sorry.
That's a semaphore, right?
Sorry.
So here you have read a few things. Yeah, lock is I mean since you have just mentioned, you are still to do that. Lock is more on when you are kind of using an object in exclusivity, right? Yes. So you have an object. So you have given you have 5 printers and 20 machines, and the print jobs are being fired, right? In parallel, right? So I mean, you cannot get mixed up that when one printer is printing, it takes up another job. So when you fire it on a printer, you have to lock that printer, finish the fired job, right? So lock is a concept which is significantly. I mean, we always often gets a little bit mixed up as to that. Lock also gives a sense of synchronization. I mean, it is possible to synchronize a few things based on lock, but you synchronize things based on lock when it is when the synchronization is based on an object. And
Conditions or semaphores?
Conditions, I mean, controls conditions are basically semaphores, right?
Yes,
You'll study them in depth in operating system and
yeah,
distributed
now I
system.
can see how you can use the diagram for modeling all of these.
Right.
Yeah,
So that is,
general.
so I'm just trying to leave certain, future pointers with you, just to say that, well, maybe the kind of examples that we are doing right now, of course, we are not trying to do any assignment which has concurrent programming or parallel programming, the kind of things like booking or the kind of example systems given to you in the laboratory, more or less are sequential systems. I mean, more or less expectation wise, but I'm just leaving pointers to you so that maybe not now, but later on when you get exposed to these systems, you'll be able to relate. Well,
Come back.
this is the modeling diagram. So let me go
Yeah.
back and check it again, and I can do a very concrete modeling diagram in terms of that. So try to take the behavior in a totality.
Yes.
One is on the sequencing part of time. One is on the placement part of the space. One is in terms of the control and object flow, how you can manage that. And one is at the end of the day, can you actually, when you are doing something or you're waiting for somebody, can you represent them in terms of a finite number of states so that your system representation becomes more compact. So that's kind of the overview of what you look the whole modeling as. So that's the perspective I'm trying to give. That's the reason there are a lot of finer detailed models which I'm skipping here, because certainly we cannot spend the entire semester discussing only UML. So let me just go back and try to close the rest. So we talked about controls. The next is objects. Okay, skip the recap. So an object in an abstract object is kind of an abstract activity node. So that can be used to define object flows. So object, we were just looking at, okay, this is an order, this is a specification, but it could have a lot of other properties also. For example, this is kind of the you can see this is kind of a class diagram for object. So you can have activity parameter nodes, which is basically the parameters of the activity which will come from there. So you you are specializing on this hierarchy. You can have a pin which says we'll see input and output pins as to kind of, they are used very extensively in software modeling to say that this is the pin is something where you can hook to an object. You could have a central buffer node because you may have a pool of objects. Very often you have pool of objects, and that could specialize to a data store also. I mean, like a database which has your objects, and expansion nodes. So just a kind of overview that I'd like to give. So recap, an object node is like this with a rectangle which goes from one activity to the other. So you said that you have an order passing from fill order to review order. So you are saying that, well, your invisible token flows for the control, but in reality, you are passing on an order from fill order to the review order. Okay. So you can also put this in as a kind of, instead of showing it on the arc, you could put this in along with the activity and say it's an object node for input and output. So you say add to shopping cart, the control comes in and you draw a pin here. This is called a pin, and you write the name of the object. So you're saying that what comes in is an item, what goes out is an invoice, right? So makes it more explicit and easier to follow, because if I go back, slide 6, if I go back here, then it's kind of the main thing you want to talk about is control flow, but on that you're putting the object. But you can just say that, well, fill order, you can put a pin here, output pin, which says is order. You can put an input pin, which say is an order, and rest of it is whatever you want to do in the control flow, because there on the control flow itself, you may have concurrency and decisions, all of that coming in, right? So it's how the object is demarcated. And it could be put into the pin could be used also to put objects into some store. So you're saying patient admission. So output pin is patient. So what a patient is going out, and patient object is going out, and it goes into a data store patient. So kind of patient is admitted means there is a database of patients where the patient has got registered, right? So all incoming tokens are stored in this data store. So that's the concept of a central buffer whenever you need that. So you are making, you are doing bookings. Once you have completed a booking, you have a booking object created. And then, you would probably often need an MIS report at the end of the session to say that what are the bookings this particular booking clerk has done, this booking executive has done. So you will keep on, and naturally you need the booking information for actually managing the baths, seats, etc. So once this has been created, it goes into a booking database. So that kind of a situation. So that's a central store requirement. So this is the processing order, make cell. It goes into the customer database, and then it goes out from the ship item. It goes out for welcome packet on certain conditions. So all sold orders will be shipped, but maybe for select customers who are your premium customers, you might send a special packet, or the customer. Yeah, here it is a welcome packet. So you say order.customer.previous order. So order is a data store, and the particular order that you have processed for shipping from the data store. Then .customer is the customer of the order, and you see whether there is previous order for that customer. If that is 0, then this is the first order placed by the customer. So you kind of build a relationship by sending a welcome packet and so on. Similarly, here you are assembling carts. So the pin, you can see that little differently it is drawn. Earlier it was outside the box, it is on the line. Both notations are allowed. Goes into the central buffer. There's a collection of assembled cars, and then it goes out to sell the car or refresh company cars and so on. Right? Multiple of these. Now, the other than object, so you have seen the activity flows, we have seen control, we have seen objects. Other than that, you can actually have actions. So action is a named element which represents a single atomic step within an activity, which is not further decomposed within the activity. You have seen that I can have an activity, and that can have another activity chart, that can have another activity chart, the three-pronged, shovel we had. So you can say the process order. So an example of a action language for account A, accounts, verify balance, and for so you're verifying balance. That's the action you are doing. Naturally, when you do that, you will write it in pseudo language, or often you may have chosen your implementation language, and you would express it in that language. There could be pre and post conditions locally for this action. So you're doing process order, and you're saying that local precondition is all information is provided, and the order was prepaid, which is obvious, but this is what you make it explicit. You can represent that, well, I can do this activity and take this action provided this condition is satisfied. And what happens after you have done this activity? The order is complete and verified. So that's the post condition. So that's what are the actions that you can. This is in terms of dispensing drinks. So the input pin object is drink name. Output pin object is the drink itself. The local precondition is drink selected is low calorie. The local post condition is drinks dispensed is low calorie. So there could be a variety of types. This is just showing you. I just picked up. I tried to pick up as many of diverse domain examples by searching the net. So you can. These are some of the ways the activity diagram can be used. This is another example on order processing. You receive the order request. This is a object, which is object node. You have approved payment, and then you submit the order. Approved payment has this symbol. So approved payment, this is approved payment. which is expanded here. You get the order, which is object, calculate total, authorize credit card, update order status, and then you finally have the order, right? So, and this is showing in stages as to the different ways you can put all these together. So you can just have a order object on the link, or you can show it in terms of the output and input pin. You can put attributes, certain attributes on this, the transformation, which is order cost. You could put guard condition, like the status of the order. It's pending here, it is approved here, you have not being shown earlier, and approved payment is what you saw earlier, right? So these are just different examples showing you. Okay, so that was about the activity diagram. There are some examples here for the leave system. You can read through later on. So what we will skip this interaction overview diagram. Do not have time for so much. So what we have seen so far are 4 kinds of behavioral diagram: abstraction, use case, temporal message information, sequence diagram, spatial message information, collaboration, coordination between objects, communication diagram, and we have seen algorithmic details coming in terms of the activity diagram. Now, not final, I should not say. The last that we will discuss, there are several more, but we do not have time for so much. The important ones is a state machine diagram. State machines, you know, right? You have done finite automaton, right?
Yes, sir.
Finite state machine, FSM, and all that you have done. So you have a basic understanding of what a state machine is. So we know that, and what you know is some kind of a very simple representation where we have states. What is a state machine? Finite state machine, or we simply call state machine, assuming that infinite things, at least in the real world modeling, cannot happen. So you have states where your system could be. You have input, and based on the input, the state makes a transition to another state. You have a start state where everything starts, and you have one or more goal state or end state or final state where the state machine starts, finishes the actions. Optionally, a state transition could also lead to an output being generated. And you must have seen the Moore and Milley ways of representing state machines, and state transition diagrams and state transition tables and so on. But here we will use that same concept, but we will take it to a little bit of higher level of hierarchy. That is, state machine FSM in that way will come finally at the LLD level, or maybe at the fag end of the HLD, high level, or most often in the low level design. Okay, I have a state machine. You will go and study as to if I finally have to implement this, these are the states, how I represent, how the transitions. But here we will talk about state machines at a little bit higher level of abstraction, right, where states could be loaded. They could be just a state that is representing certain combination of information, or it could be something more complex. It could be a collection of states. A state machine itself could be a state of another state machine, and so on. So we will broadly in UML diagram, we will broadly look at behavioral and protocol state machine. We'll see that the traditional FSM that we have seen earlier is will be a special case of these state machines, but these are, and there's something very close to this which has also been used quite often in modeling, and in your subsequent papers you might come across that, which is called state chart or state chart diagram, which is very similar to this. Towards the end I'll try to comment what the state charts are. So let's start with the behavioral state machine. Now, what is a state of an object? You know very well, we have talked about this from almost the very beginning, that it's a combination of values that its data member has, right? So I have a complex object. Its state is a value of the real part as well as the imaginary part, right? And the behavior of the object are the set of operations that can be done. You know all of this. We are talking about the client server models still. We are at this level in the analysis phase primarily, where we are the state chart diagram or state machine diagram is what will come in here in the behavioral model. So what are the state machine diagrams? A state machine diagram is a behavioral diagram which shows the discrete behavior of a part of a design system through finite state transitions. Your entire system may not be a state machine. It may be, it may not be. But often certain parts of the system are better described in terms of state machines. And we will use two kinds of representations here. One is called the behavioral state machine, another is called the protocol state machine. And as you know well, a state machine diagram consists of states and transitions between them. So what is a behavioral state machine? It is a specialization of behavior, as the name suggests, and is used to specify discrete behavior of a part of a design system through finite state transitions. So it's kind of a traversal graph. So it could be owned by a behavior class, which is called its context. Like a state machine by itself may not mean much because it has to talk about variety of different properties.
Sir, you are not audible.
Am I audible now? I had lost connection. Am I audible?
Yes, sir.
The connection is so frustrating every day. So I hope the presentation is visible. We are on slide 11, module 32.
You were in the earlier slide, in slide 10.
Am I now in slide 11?
Yes, sir. The connection lost during the previous slide.
Yeah, now I'm in slide 11. You can see that,
Yes,
right?
sir. Yes, sir. Yeah.
Okay. So this is an, I will start with some examples of state machines that are very easy to model. For example, you are talking about a very abstract behavior at a bank ATM. So what is a normal state when the ATM is there? It's an idle state. Nothing is happening, right? And then somebody comes in, puts the card in. As you put the card in, a transaction process starts. So it gets into a state, let's say active state. Now, this is where you have to note the level of abstraction. That in this state, a lot of things again can happen. right? The person has to choose language. The person has to just tell what he or she has to do. He has to put the pin. It has to, if withdraw, if balance, if deposit, all sorts of things. But that whole thing, all those details can be represented again through states, but we are not doing that. We are looking at a certain abstraction. We are looking at what is the state of the machine. The machine was idle, now it is being used, so it is active, right? So all of that happens. So when does it that behavior state of being active end? When the transaction is done, that is done means successfully done, or when for some reason the person or the ATM decides to cancel the transaction. The person can cancel, or ATM could also cancel that. Okay, your PIN is wrong, and it goes back to the idle state. So that's how you kind of represent. The machine could go kaput. If it does, then it has put as out of service. So a service is required, and when it gets fixed, it gets back to idle. Very simple diagram to show what is the overall behavior. Let us see another. This is a temperature controller, which can cool if it is hot, which can heat if it is cold. So it is ideally in the idle state. That's where it stays. If it is too hot, it turns on cooling, keeps on checking the temperature. Once it is adequately cool, it comes back. Okay, it comes back to the idle state. That's what you must have seen the air conditioners in that. Similarly, if it is too cold, it turns on heating, heats up, monitors temperature, and when it's adequate, it goes back to idle with okay. In any of the heating or cooling, there may be some defect in the machine, some error. So then it goes to the error state. The error may be removed by resetting or by repairing the machine. It comes back to the idle state. So these are kind of very simple ways to represent the abstract concept of high level of state transitions that could happen in the behavior of a system. So a behavioral state machine will consist of vertices and behavioral transitions. The vertex is named element, which is an abstraction of a node in a state machine graph. Quite clear. And it can be a source or destination of any number of transitions, right? Any number of transitions could come in, any number of transitions could go out. And there could be subclasses of vertex, which are behavioral state or pseudo state. So state is a vertex which models a situation during which some invariant condition holds. Right. Often that condition may be implicit. For example, a state idle for the ATM was a condition when the ATM is not being used. The condition active is a state when the ATM is being used, some keys are being pressed, some process flow is happening, some activity is going on, and so on. In this way, right? So behavioral state models a situation during which some invariant condition will hold. So that invariant could represent a state situation such as object waiting for some external event to happen. That is one. For example, in the idle state, the ATM is waiting for an external request by the customer, for the card to be put in or the input screen to be tapped and so on. Or it could model dynamic conditions such as a process of performing some behavior. The printer is in busy state because it is printing some document, right? So it will continue to remain in that state because it is that dynamic condition of printing is continuing. And there could be various kinds of states like simple state, composite state, and sub-machine state. A simple state is one which does not have substates. We have 2 minutes. So let me stop at this point. So that because we will not be able to complete this, we'll have to take it up tomorrow anyway. So let me stop here and get back in the last 2 minutes. Let me ask if there are any questions from any of you on the state machine part. Then we can answer. Otherwise, we'll close the day. Any questions? No? Okay then. Thank you very much. So we will have a nice day. We will continue tomorrow. Tomorrow, I hope that we'll be able to complete the state machine diagram discussion. And with that, I'll kind of close the discussion on UML. There are a lot still remaining, but we do not have time because we need some time to discuss some of the other very important aspects of software engineering, particularly testing and validation and those kind of things. Thank you very much. See you again tomorrow.